Polygon surfaces. In this video, we are going to see about polygon surfaces. Boundary representations, BREPs. Objects are represented as a collection of surfaces. 3D object representation is divided into two categories. Space partitioning representations. It describes a 3D object as a set of surfaces that object interior from the environment. It is used to describe interior properties by partitioning the spatial region containing an object into a set of small, non-overlapping, contiguous solids, that is usually cubes. The most commonly used boundary representation for a 3D graphics objects is a set of surface polygons that enclose the object interior. Many graphics systems use this method. Set of polygons are stored for object description. This simplifies and speeds up the surface rendering and display of object, since all surfaces can be described with linear equations. The polygon surfaces are common in design and solid modeling applications, since their wireframe display can be done quickly to give general indication of surface structure. Then realistic scenes are produced by interpolating shading patterns across polygon surface to illuminate. Polygon tables. In this method, the surface is specified by the set of vertex coordinates and associated attributes. As shown in the figure, there are 5 vertices from V1 to V5. Each vertex stores x, y, and z coordinate information, which is represented in the table as V1 is to x1, y1, z1. The edge table is used to store the edge information of polygon. In the figure, edge E1 lies between vertex V1 and V2, which is represented in the table as E1, V1, V2. Polygon surface table stores the number of surface present in the polygon. From the following figure, surface S1 is covered by edges E1, E2 and E3, which can be represented in the polygon surface table as S1, E1, E2 and E3. Plane equation. The equation for plane surface can be expressed as ax plus by plus cz plus d is equal to 0, where x, y, z is any point on the plane and the coefficients a, b, c and d are constants describing the spatial properties of the plane. We can obtain the values of a, b, c and d by solving a set of 3 plane equations using the coordinate values for 3 non-collinear points in the plane. Let us assume that 3 vertices of the plane are x1, y1, z1, x2, y2, z2 and x3, y3, z3. Let us solve the following simultaneous equations for ratios a by d, b by d and c by d. You get the values of a, b, c and d. To obtain the above equations in determinant form, apply Cramer's rule to the above equations. For any point x, y, z with parameters a, b, c and d, we can say that ax plus by plus cz plus d not equal to 0 means the point is not on the plane. Ax plus by plus cz plus d lesser than 0 means the point is inside the surface. Ax plus by plus cz plus d greater than 0 means the point is outside the surface. Polygon meshes. 3D surfaces and solids can be approximated by a set of polygon and line elements. Such surfaces are called polygonal meshes. In polygon mesh, each edge is shared by at most 2 polygons. The set of polygons or faces together form the skin of the object. This method can be used to represent a broad class of solids or surfaces in graphics. A polygonal mesh can be rendered using hidden surface removal algorithms. The polygon mesh can be represented by 3 ways: explicit representation, pointers to a vertex list, pointers to an edge list. Advantages: it can be used to model almost any object. They are easy to represent as a collection of vertices. They are easy to transform. They are easy to draw on computer screen. Disadvantages: curved surfaces can only be approximately described. It is difficult to simulate some type of objects like hair or liquid. Quadric surfaces. In this video, we are going to see about quadric surfaces. Quadric surfaces. A frequently used class of objects is the quadric surfaces, which are described with second-degree equations, that is, quadratics. They include spheres, ellipsoids, tori, paraboloids, and hyperboloids. Quadric surfaces, particularly spheres and ellipsoids, are common elements of graphics scenes, and they are often available in graphics packages as primitives from which more complex objects can be constructed. Sphere. In Cartesian coordinates, a spherical surface with radius r centered on the coordinate origin is defined as a set of points x, y, z that satisfy the equation x square plus y square plus z square is equal to r square. We can also describe the spherical surface in parametric form using latitude and longitude angles. The parametric representation in equation provides a symmetric range for the angular parameters theta and pi alternatively. We could write the parametric equation using standard spherical coordinates, where angle phi is specified as the colatitude then phi is defined over the range 0 lesser than or equal to phi lesser than or equal to pi, and theta is often taken in the range 0 is lesser than or equal to theta lesser than or equal to 2 pi. We could also set up the representation using parameters u and v defined over the range from 0 to 1 by substituting phi is equal to pi u and theta is equal to 2 pi v. Ellipsoid. An ellipsoidal surface can be described as an extension of a spherical surface where the radii in three mutually perpendicular directions can have different values. The Cartesian representation for points over the surface of an ellipsoid center on the origin is, and a parametric representation for the ellipsoid in terms of the latitude angle phi and the longitude angle theta. Torus. A torus is a donut-shaped object. It can be generated by rotating a circle or other conic about a specified axis. The Cartesian representation for points over the surface of a torus can be written in the form where r is any given offset value. Parametric representation of a torus are similar to those for an ellipse, except that angle phi extends over 360 degrees using latitude and longitude angles phi and theta. We can describe the torus surface as the points that satisfy spline representation. In this video, we are going to see about spline representation. To produce a smooth curve through a designated set of points, a flexible strip called spline is used. Such a spline curve through a designated set of points, a flexible strip called spline is used. Such a spline curve can be mathematically described with the piecewise cubic polynomials functions whose first and second derivatives are continuous across the various curve sections. We can specify a spline curve by giving a set of coordinate positions called control points, which indicates the general shape of the curve. When polynomial sections are fitted so that the curve passes through all control points as shown in the figure A, the resulting curve is said to interpolate the set of control points. On the other hand, when the polynomials are fitted to the path which is not necessarily passing through all control points, the resulting curve is said to approximate the set of control points. This is illustrated in the figure B. Geometric and parametric continuity. To ensure a smooth transition from one section of a piecewise parametric curve to the next, we can impose various continuity conditions at the connection points. We see parametric continuity and geometric continuity conditions. In geometric continuity, we require parametric derivatives of two sections to be proportion to each other at their common boundary instead of equal to each other. Parametric continuity is set by matching the parametric derivatives of adjoining two curved sections at their common boundary. In zero-order parametric continuity, given as c degree, it means simply the curve meet, and same is for zero-order geometric continuity. In first-order parametric continuity, called as C1, means that first parametric derivatives of the coordinates functions for two successive curved sections are equal at the joining point, and geometric first order continuity means the parametric first derivatives are proportional at the intersection of two successive sections. Second order parametric continuity, or C2 continuity, means that both the first and second parametric derivatives of the two curved sections are same at the intersection, and for second order geometric continuity, or C2 continuity, means that both the first and second parametric derivatives of the two curved sections match at the joining positions. Under C2 continuity, curvature of the two curved sections match at the joining positions. Derivative. Spline specifications. There are three basic ways of specifying spline curve. We can state the set of boundary conditions that are imposed on the spline. We can state the matrix that characteristics the spline, or we can state the set of blending functions that calculate the positions along the curve path by specifying combination of geometric constraints on the curve. Why to use cubic polynomials? Polylines and polygons are first degree, piecewise linear approximation to curves and surface respectively. But these lower degree polynomials give too little flexibility in controlling the shape of the curve. The higher degree polynomials give reasonable design flexibility, but introduce unwanted wiggles and also require more computation. For this reason, the third degree polynomials are most often used for representation of curves. For this reason, the third degree polynomials are most often used for representation of curves. These polynomials are commonly known as cubic polynomials. We can describe the parametric cubic polynomials that is to be fitted between each pair of control points with the following set of equations. These polynomials are commonly known as cubic polynomials. We can describe the parametric cubic polynomials that is to be fitted between each pair of control points with the following set of equations. We do this by setting enough boundary condition at the joints between curved sections so that we can obtain numerical values for all the coefficient. Hermite curve. In this video, we are going to see about Hermite curve. With Bezier curves, the set of control points implicitly specifies the tangents at the curve ends. Recall that the line between the first two control points is tangent to the Bezier curve start, and the line between the last two control points is tangent to the Bezier curve end. Hermite curves are specified by the start point and end point and the tangents at those points. The process then uses a set of blending functions to determine the points on the curve based on these values. A Hermite curve is given by the equation 1, where the two endpoints are P0 and P1 and their associated tangents are T0 and T1 respectively. C of t is equal to 2 into t cube minus 3 into t square plus 1 into p0 plus of minus 2 into t cube plus 3 into t square into p1 plus of t cube minus 2 into t square plus t into t0 plus of t cube minus t square into t1. The blending functions applied to each of these components behave similarly to those in Bezier and B-spline curves. In this equation, when t has a value of 0.0, the first blending function for P0 has a value of 1.0 and all the rest will be 0. When t has a value of 1.0, only the blending function for P1 has a value of 1.0 and all the rest are 0. Figure shows the impact that the direction of the tangent vector can have the shape of the curve. In each of the curves in this figure, the only thing that changes is the direction of the initial vector. The two curves at the top and bottom of the right column use the same two tangent vectors, but they are reversed. The initial tangent in the top curve becomes the final tangent in the bottom curve, and vice versa. Hermite curves are invariant under the transformations of rotation scale and translation. Applying these transformations to the endpoints and tangent vectors will effectively apply these transformations to the entire curve. Bezier curve. In this video, we are going to see about Bezier curve. Bezier curve is another approach for the construction of the curve. A Bezier curve is determined by a defining polygon. Bezier curves have a number of properties that make them highly useful and convenient for curve and surface design. They are also easy to implement. Therefore, Bezier curves are widely available in various CAD systems and in general graphic packages. Properties of Bezier curve. The basic functions are real. Bezier curve always passes through the first and last control points, that is, curve has same endpoints as the guiding polygon. The degree of the polynomial defining the curve segment is 1 less than the number of defining polygon point. Therefore, for 4 control points, the degree of the polynomial is 3, that is cubic polynomial. The curve generally follows the shape of the defining polygon. The direction of the tangent vector at the endpoints is the same as that of the vector determined by first and last segments. The curve lies entirely within the convex hull formed by 4 control points. The convex hull property for a Bezier curve ensures that the polynomial smoothly follows the control points. The curve is invariant under an affine transformation. In cubic Bezier curve, 4 control points are used to specify complete curve. Unlike the B-spline curve, we do not add intermediate points and smoothly extend Bezier curve, but we pick 4 more points and construct a second curve which can be attached to the first. The second curve can be attached to the first curve smoothly by selecting appropriate control points. The figure shows the Bezier curve and its 4 control points, as shown in the figure. Bezier curve begins at the first control point and ends at the 4th control point. This means that if we want to connect 2 Bezier curves, we have to make the first control point of the second Bezier curve match the last control point of the first curve. We can also observe that at the start of the curve is tangent to the line connecting first and second control points. Similarly, at the end of curve, the curve is tangent to the line connecting the third and fourth control point. This means that to join 2 Bezier curves smoothly, we have to place the third and the fourth control points of the first curve on the same line specified by the first and second control points of the second curve. The Bezier matrix for periodic cubic polynomial is another approach. Another approach to construct the Bezier curve is called midpoint approach. In this approach, the Bezier curve can be constructed simply by taking midpoints. In midpoint, approach midpoints of the lines connecting 4 control points A, B, C, D are determined AB, BC, CD. These midpoints are connected by line segments and their midpoints ABC and BCD are determined. Finally, these 2 midpoints are connected by line segments and its midpoint ABCD is determined. The point ABCD on the Bezier curve divides the original curve into 2 sections. This makes the point A, AB, ABC and ABCD are the control points for the first section, and the points A, B, C, D, BCD, CD and D are the control points for the second section. By considering 2 sections separately, we can get 2 more sections for each separate section, that is, the original Bezier curves. This process can be repeated to split the curve into smaller sections until we have sections so short that they can be replaced by straight lines, or even until the sections are not bigger than individual pixels. B-spline curve. In this video, we are going to see about B-spline curve. we have seen that a curve generated by using the vertices of a defining polygon is dependent on some interpolation or approximation scheme to establish the relationship between the curve and the polygon. This scheme is provided by the choice of basis function. The Bezier curve produced by the Bernstein basis function has a limited flexibility. First, the number of specified polygon vertices fixes the order of the resulting polynomial which defines the curve. The second limiting characteristics are that the value of the blending function is non-zero for all parameter values over the entire curve. Due to this change in one vertex changes the entire curve, and this eliminates the ability to produce a local change within a curve. There is another basis function called the B-spline basis, which contains the Bernstein basis as a special case. The B-spline basis is non-global. It is non-global because each vertex Bi is associated with a unique basis function. Thus, each vertex affects the shape of the curve only over a range of parameter values where its associated basis function is non-zero. The B-spline basis also allows the order of the basis function, and hence the degree of the resulting curve is independent on the number of vertices. It is possible to change the degree of the resulting curve without changing the number of vertices of defining polygon. If P of u be the position vectors along the curve as a function of the parameter u, a B-spline curve is given by where the Bi are the position vectors of the n+1 defining polygon vertices and the Nik are the normalized B-spline basis functions. For the ith normalized B-spline basis function of order k, the basis function Nik are defined as the values of xi are the elements of a knot vector satisfying the relation xi lesser than or equal to xi plus 1. The parameter u varies from u minimum to u maximum along the curve P of u. There are three types of k-knot vector: uniform, open uniform, non-uniform. In a uniform knot vector, individual knot values are evenly spaced. For example, 0, 1, 2, 3, 4. For a given order k, uniform knot vectors give periodic uniform basis functions for which Nik of u is equal to Ni minus 1k of u minus 1 is equal to Ni plus 1k of u plus 1. An open uniform knot vector has multiplicity of knot values at the ends equal to the order k of the B-spline basis function. Internal knot values are evenly spaced. Examples are k is equal to 2 of 0, 0, 1, 2, 3, 3. K is equal to 3 of 0, 0, 0, 1, 2, 3, 3, 3. K is equal to 4 of 0, 0, 0, 0, 1, 2, 2, 2, 2. Generally, an open uniform knot vector is given by xi is equal to 0, 1 lesser than or equal to I lesser than or equal to k. Xi is equal to I minus k. K plus 1 lesser than or equal to I lesser than or equal to n plus 1. Xi is equal to n minus k plus 2. N plus 2 lesser than or equal to I lesser than or equal to n plus k plus 1. In fact, when the number of defining polygon vertices is equal to the order of the B-spline basis and an open uniform knot vector is used, the B-spline basis reduces to the Bernstein basis. Hence, the resulting B-spline curve is the Bezier curve. Bezier surface. In this video, we are going to see about Bezier surface. The discussion of Bezier curves and B-spline was designed to help you understand these methods of specifying complex curves because they are the basis for two methods for specifying curved surface. They are useful for sweeping out the shape of objects. They are useful for specifying motion in animated sequences. Bezier surfaces. Bezier surfaces merely apply the Bezier curve method in two directions to form the surface, where a Bezier curve is specified with 4 control points along the length of the curve. A Bezier surface is specified by 16 control points in a two-dimensional grid that has 4 control points on each side. Figure shows a Bezier surface with its control points at the intersections of the black lines. When working with this grid of control points, the two perpendicular directions for the control points are referred to as u and v directions, where u is the parameter that moves through the row of control points and v is the parameter that moves through the columns of control points. Both of these parameters have the range 0, 1. Bezier surfaces use the same curve blending functions in both the u and v direction. This means that the control point P0 is used B0 of u and B0 of v, and the control point P2 is used with B2 of u and B1 of v. In general, Pij is used with Bi of u and Bj of v, so that the full surface equation is given by equation 1. Because the surface is made up of Bezier curves in two directions, the properties of those curves also apply to the surfaces. First, where a Bezier curve interpolates along that entire edge with at least g0 continuity. Now, if the 3 points in the u direction centered at each of these shared control points are all on the same line, the surfaces will exhibit g1 continuity along that shared edge. Lastly, if the distance between the control points in each set are the same, the shared edge will exhibit C1 continuity. Figure showed that to preserve continuity across a join point, moving a control point on one side required a move of the control point on the other side in the opposite direction. The same is true of a Bezier surface. In this case, the change occurs with any of the four sets of points along a shared edge. If there are a four surfaces that share a corner point, changes around that corner point will propagate to all three of the other surfaces. For example, if a Bezier surface is divided in half horizontally, any patches that meet along the left and right sides should also be divided horizontally to allow changes to properly propagate across the object. B-spline surface. In this video, we are going to see about B-spline surface. B-spline surfaces are constructed from curves in the same way that Bezier surfaces are. We again have a two-dimensional grid of control points that determine the shape of the B-spline surface. The grid of points is used with B-spline blending functions in two directions. All of the things that were discussed relative to B-spline curves also apply to B-spline surfaces. A surface is extended by adding a control point to each of the curves that run in that direction. Beginning with a grid of control points that is 4 by 4, extending this surface requires 4 additional points to make the grid 4 by 5 control points. To extend the surface in the other direction, an additional 5 control points are needed so that the grid becomes 5 by 5 control points. The B-spline surface will exhibit local control in the U and V directions. Moving one control point will change the surface shape in a small neighborhood around the control point that was moved. Basic illumination model. In this video, we are going to see about basic illumination model. Two major terms of light sources are point and infinitely distant. Radial intensity attenuation, that is I by d square. Point source with I by d square attenuation does not always produce realistic results. Produces too much intensity variation for near objects and not enough for distant. Fi radial attenuation is equal to 1.0 if source is at infinity. I by A naught plus A1 di plus A2 di square if source is local. The direction light sources and spotlight effects. An object illuminated by a directional point light source. V object dot V light is equal to cos alpha. Within spotlight, if cos alpha greater than or equal to cos theta g. Outside spotlight, if cos alpha lesser than cos theta g. Angular intensity attenuation. F angular attenuation is equal to cos to the power ai phi 0 degree lesser than or equal to phi lesser than or equal to theta. Fi angular attenuation is equal to 1.0 if source is not a spotlight, 0.0 if V object dot V light is equal to cos alpha lesser than cos theta g. VObject dot VLight the whole power g, otherwise. Diffuse illumination. In this video, we are going to see about diffuse illumination. Diffuse illumination. An object's illumination is an important as its surface properties in computing its intensity. The object may be illuminated by light which does not come from any particular source but which comes from all directions. When such illumination is uniform from all directions, the illumination is called diffuse illumination. Usually, diffuse illumination is a background light which is reflected from walls, floor, and ceiling. When we assume that going up, down, right and left is of same amount, then we can say that the reflections are constant over each surface of the object and they are independent of the viewing direction. Such a reflection is called diffuse reflection. In practice, when object is illuminated, some part of light energy is absorbed by the surface of the object, while the rest is reflected. The ratio of the light reflected from the surface to the total incoming light to the surface is called coefficient of reflection or the reflectivity. It is denoted by R. The value of R varies from 0 to 1. It is closer to 1 for white surface and closer to 0 for black surface. This is because white surface reflects nearly all incident light, whereas black surface absorbs most of the incident light. Lambert's law. We have seen that the diffuse reflections from the surface are scattered with equal intensity in all directions, independent of the viewing direction. Such surfaces are sometimes referred to as ideal diffuse reflectors. They are also called Lambertian reflector, since radiated light energy from any point on the surface is governed by the Lambert's cosine law. This law states that the reflection of light from a perfectly diffusing surface varies as the cosine of the angle between the normal to the surface and the direction of the reflected ray. Thus, if the incident light from source is perpendicular to the surface at a perpendicular point, that point is fully illuminated. On the other hand, as the angle of illumination moves away from the surface normal, the brightness of the point drops off, but the points appear to be squeezed closer together, and the net effect is that the brightness of the surface is unchanged. In other words, we can say that the reduction in brightness due to cosine of angle gets cancelled by increasing the number of light emitting points within the area of view. As we move further from the viewport, the light coming from the surface spreads over a large area. This area increases by the square of distance. Thus, the amount of light reaching the eye decreases by the same factor. This factor is compensated by the size of the object. When object is moved further from the viewport, it appears smaller. Therefore, even though there is less light, it is applied to a smaller area on the retina, and hence the brightness of the surface remains unchanged. The expression for the brightness of an object is illuminated by diffuse ambient or background light can be given as I ambient diffuse is equal to KAIA. Using above equation, it is possible to create light or dark scenes or gray shaded objects. But in this simple model, every plane on a particular object will be shaded equally. The real shaded object does not look like this. For more realistic shading model, we also have to consider the point sources of illumination. Point source illumination. In this video, we are going to see about point source illumination. Point source emits rays from a single point and they can approximate real-world sources as a small incandescent bulbs or candles. A point source is a direction source whose all the rays come from the same direction. Therefore, it can be used to represent the distant sun by approximating it as an infinitely distant point source. The modeling of point sources requires additional work because their effect depends on the surface's orientation. If the surface is normal, that is perpendicular to the incident light rays, it is brightly illuminated. The surfaces turned away from the light source, that is oblique surfaces, are less brightly illuminated. For oblique surfaces, the illumination decreased by a factor of cos I, where I is the angle between the direction of the light and the direction normal to the surface plane. The angle I is known as angle of incidence. The factor cos I is given as cos I is equal to NL. Considering both diffuse illumination and point source illumination, the shade of the visible surface of an object is given as I illumination diffuse is equal to Ka Ia plus Kd Il cos I is equal to Ka Ia plus Kd Il NL. Shading algorithm. In this video, we are going to see about shading algorithm. In general, shading in computer graphics means to compute the color of an object at certain points. The method that computes this color is called shading model. The shading algorithm specifies at which points of the object the shading model is applied. Since the very beginning of computer graphic shading models and algorithm have been proposed. A good survey of models and algorithms is given in Clausen 1988. Here, we will not discuss the various shading models, only the most important shading algorithms will be enumerated. In this section, we discuss more efficient shading methods for surfaces defined by polygons. Each polygon can be drawn with a single intensity or with different intensity obtained at each point on the surface. Various shading methods. Constant intensity shading, Gauss shading, Pong shading, half-tone shading, dithering techniques. Constant intensity shading, Gauss shading, Pong shading, half-tone shading, dithering techniques. Constant intensity shading. In this video, we are going to see about constant intensity shading. The fact and simplest method of shading polygon is constant shading, also known as faceted shading or flat shading. The entire polygon is then displayed with the single intensity value. This method is valid for the following assumptions. The light source is at infinity, so NL is constant across the polygon face. The viewer is at infinity, so VR is constant over the surface. The polygon represents the actual surface being modeled and is not an approximation to a curved surface. If either of the first two assumptions are not true, still we can use constant intensity shading approach. However, we require some method to determine a single value for each of L and V vectors. Gauss shading. In this video, we are going to see about Gauss shading. In this method, the intensity interpolation technique developed by Gauss is used, hence the name. The polygon surface is displayed by linearly interpolating intensity values across the surface. Here, intensity values for each polygon are matched with the values of adjacent polygons along the common edges. This eliminates the intensity discontinuities that can occur in flat shading. By performing following calculations, we can display polygon surface with Gauss shading. Determine the average unit normal vector at each polygon vertex. Apply an illumination model to each polygon vertex to determine the vertex intensity. Linearly interpolate the vertex intensities over the surface of the polygon. We can obtain a normal vector at each polygon vertex by averaging the surface normals of all polygons sharing that vertex. There are three surfaces normals N1, N2 and N3 of polygon sharing vertex V. Therefore, normal vector at vertex V is given as NV is equal to N1 plus N2 plus N3 by modulus of N1 plus N2 plus N3. In general, for any vertex position V, we can obtain the unit vertex normal by equation, where n is the number of surface normals of polygons sharing that vertex. The next step in Gouraud shading is to find vertex intensities. Once we have the vertex normals, their vertex intensities can be determined by applying illumination model to each polygon vertex. Finally, each polygon is shaded by linear interpolating of vertex intensities along each edge and then between edges along each scan line. For each scan line, the intensity at the intersection of the scan line with a polygon edge is linearly interpolated from the intensities at the edge endpoints. The polygon edge with endpoint vertices 1 and 2 is intersected by the scan line at point A. The intensity at point A can be interpolated from intensities I1 and I2 as Similarly, we can interpolate the intensity value for right intersection, that is point B, from intensity values I2 and I3 as Once the intensities of intersection points A and B are calculated for a scan line, the intensity of an interior point can be determined as During the scan conversion process, usually incremental calculations are used to obtain the successive edge intensities values between the scan lines and to obtain successive intensity along a scan line. This eliminates the repetitive calculations. If the intensity at edge position x, y is interpolated as then we can obtain the intensity along this edge for the next scan line y-1 as Similarly, we can obtain intensities at successive horizontal pixel positions along each scan line. Advantages: it removes the intensity discontinuities exist in constant shading model. It can be combined with a hidden surface algorithm to fill in the visible polygon along each scan line. Disadvantages: highlights on the surface are sometimes displayed with anomalous shapes. The linear intensity interpolation can result bright or dark intensity streaks to appear on the surface. These bright or dark intensity streaks are called Mach bands. The Mach band effect can be reduced by breaking the surface into a greater number of smaller polygons. Sharp drop of intensity values on the polygon surface cannot be displayed. Pong shading. In this video, we are going to see about Pong shading. Pong shading. Pong shading, also known as normal vector interpolation shading, interpolates the surface normal vector n instead of the intensity. By performing following steps, we can display polygon surface using Pong shading. Determine the average unit normal vector at each polygon vertex. linearly interpolate the vertex normals over the surface of the polygon. Apply an illumination model along each scan line to determine projected pixel intensities for the surface points. The first steps in the Pong shading is same as first step in the Gouraud shading. In the second step, the vertex normals are linearly interpolated over the surface of the polygon. The normal vector n for the scan line intersection point along the edge between vertices 1 and 2 can be obtained by vertically interpolating between edge endpoint normal. Like Gouraud shading, here also we can use incremental methods to evaluate normals between scan lines and along each individual scan line. Once the surface normals are evaluated, the surface intensity at that point is determined by applying the illumination model. Advantages: it displays more realistic highlights on a surface. It greatly reduces the Mach band effect. It gives more accurate results. Disadvantages: it requires more calculations and greatly increases the cost of shading steeply. Half-tone shading. In this video, we are going to see about half-tone shading. Half-tone shading. Many displays and hard copy devices are bi-level. They can only produce 2 intensity levels. In such displays or hard copy devices, we can create an apparent increase in the number of available intensities. This is achieved by incorporating multiple pixels positions into the display of each intensity value. When we view a very small area from a sufficiently large viewing distance, our eyes average fine details within the small area and record only the overall intensity of the area. This phenomenon of apparent increase in the number of available intensities by considering combined intensity of multiple pixels is known as half-toning. The half-toning is commonly used in printing black and white photographs in newspapers, magazines, and books. The pictures produced by half-toning process are called half-tones. In computer graphics, half-tone reproductions are approximated using rectangular pixel regions, say 2 into 2 pixels or 3 into 3 pixels. These regions are called half-tone patterns or pixel patterns. Dithering techniques. In this video, we are going to see about dithering techniques. Dithering refers to techniques for approximating half-tones without reducing resolution as pixel grid patterns do. The term dithering is also applied to half-tone approximation methods using pixel grids, and sometimes it is used to refer to color half-tone approximations only. Random values is added to pixel intensities to break up contours are often referred as dither noise. Number of methods are used to generate intensity variations. Ordered dither methods generate intensity variations with a one-to-one mapping of points in a scene to the display pixels. To obtain n-square intensity levels, it is necessary to set up an n into n dither matrix Dn whose elements are distinct positive integers in the range of 0 to n square minus 1. For example, it is possible to generate 4 intensity levels with D2 and it is possible to generate 9 intensity levels with D3. The matrix elements for D2 and D3 are in the same order as the pixel mask for setting up 2x2 and 3x3 pixel grids respectively. For bi-level system, we have to determine display intensity values by comparing input intensities to the matrix elements. Each input intensity is first scaled to the range 0 lesser than or equal to I lesser than or equal to n square. If the intensity I is to be applied to the screen position x, y, we have to calculate row and column numbers for the either matrix as I is equal to x mod n plus 1, j is equal to y mod n plus 1. If I greater than dn I, j, the pixel at position x, y is turned on, otherwise the pixel is not turned on. Typically, the number of intensity levels is taken to be n multiple of 2. High-order dither matrices can be obtained from lower-order matrices with the recurrence relation. Another method of mapping a picture with m into n points to a display area with m into n pixels is error diffusion. Here, the error between an input intensity value and the displayed pixel intensity level at a given position is dispersed or diffused to pixel position to the right and below the current pixel position.